Okay, guys, in this video we're going to start off the next chapter. This is chapter 12, which deals with chemical kinetics, and these are the different sections that we have here. So we're going to start off with chemical reaction rates, and the figure here, this little critter sitting on the rock sunning himself. As we know, reptiles are largely cold-blooded, and the metabolic processes that this organism here needs to survive, they require energy. Okay, and so the sun is used to help regulate these metabolic processes. Now, when I say regulate, I mean to control the rate of the chemical processes. And so let's talk about what chemical reaction rates are. So we want to be able to define a chemical reaction rate and derive rate expressions from a balanced stoichiometric equation. And then we'll need to be able to do little calculations involving reaction rates based upon experimental data given to us in different problems. So first of all, what is a reaction rate? Well, the reaction rate is related to the change in the concentration of a reactant or a product in a given amount of time. So changing concentration over a given time interval. So in order to measure chemical reaction rates, you need to be able to determine concentration data as a function of time. Generally speaking, the reactant concentrations decrease with time, and the product concentrations increase with time. And by measuring by how much a reactant's concentration decreases in a given time interval, you can determine the rate of the reaction at a given moment. By convention, our reaction rates are defined such that they are positive quantities, and in general, they are time-dependent quantities. So typical behavior is that a reaction has a fast rate at the beginning, and that reaction rate often slows down. Now, that's not the only thing that can be observed. There are some reactions for which the rate of the reaction is constant. Those are called zeroth order reactions. But in general, the reaction rate changes over the course of the reaction, usually going from fast at first to slow at longer periods of time. The units of the reaction rate are concentration per unit time. And so for our purposes, the reaction rate will be given as a moles per liter. So molarity is the concentration unit per unit time. And typically that's going to be seconds. Not always. Sometimes it'll be per minute or per hour. But usually we're going to have molarity per unit time. And in the notation that we're about to develop, we'll be using this bracket notation where the bracket represents the concentration in molarity of a given species. You'll see what I mean in a moment. So here we're making a distinction between two types of chemical reaction rates. One is called the average rate, and so this is the finite concentration change over a finite time interval, which is distinct from the so-called instantaneous rate, which is the concentration change over an infinitesimally small time interval. And so these two types of rates are illustrated on this figure. So here we've got a decomposition reaction. Hydrogen peroxide is decomposing into liquid water and oxygen gas. And what we're doing is we're following the concentration. Notice the brackets. The concentration of the peroxide as a function of time in units of hours. So that's moles per liter. So we have moles per liter along the y-axis and time on the x-axis. And we see that that concentration decreases over time, right? Because it's a reactant and it's decomposing. Now let's talk about the two types of rates that we have here, the average rate. So let's look at over some time interval, say between hour 6 and hour 18, what is the change in the hydrogen peroxide concentration? So you measure the initial value of the hydrogen peroxide concentration and the final value of the hydrogen peroxide concentration. You take the difference, so final minus initial, divided by the final time minus the initial time. Okay, so let me write that down. So we've got the delta H2O2 over delta T would be the H2O2 at whatever the final time is minus the H2O2 concentration over the initial time divided by the final time minus the initial time. So this is a rate, if you will. Now, this particular number will be negative because the change is negative. You go from a larger value to a smaller value. So this is going to end up being less than 0. Okay, so this is not quite what we want for a rate because we want our rate to be expressed as a positive number. But if you take minus the delta H2O2 divided by the change in the time interval, then that would give you what we would call a rate. And so this represents the average rate over that time interval. Now the instantaneous rate is proportional to the slope of this line that's tangent to the curve. So at this moment in time, 12 hours, there's a line that is tangent to the curve. And the slope of that line, minus the slope of that line, is equal to the instantaneous rate at that point. You'll notice that at an earlier point, say at 0 hours, the line that's tangent to the curve has a different slope. And so it has a different instantaneous rate. It also has a different finite average rate as well. And so as you go from this point to some point out here, you'll notice that the slope of the line tangent to the curve changes. It goes from a very steep slope, indicating a fast rate, to a medium slope, indicating a medium rate. Out here, the slope would be very gentle, and that would be a small rate. So the rate of the reaction changes with time. And there's a distinction between the average rate and an instantaneous rate. If you've had a calculus course and you've studied derivatives before, then the instantaneous rate would be equal to the first derivative of this concentration expressed as a function of time, the first derivative with respect to time. So that would be the instantaneous rate. Now, you're not required to know calculus for this course, so we're going to focus on the algebraic or average definition. But just note that in some of our notation, I'll mix back and forth between the two. So, in this slide, what I want to articulate is that the rate of a reaction, which will be a unique number at any given moment in time, can be expressed in terms of the rate of change for any reactant or product. And so what I'm trying to say is that the rate of the reaction, which I'm going to just use the word rate, I can express the rate in terms of a rate of change of the ammonia concentration. I could express it in terms of the rate of change of the nitrogen concentration, or I could express it in terms of the rate of change of the hydrogen concentration. Now, keep in mind that the concentration of ammonia is decreasing and the concentration of nitrogen and hydrogen are increasing. So the time derivative, the delta ammonia divided by delta T, that's going to be a negative number. But the delta N2 divided by delta T, that's going to be a positive number. So I have to come up with a way of taking into account the fact that the reactants are decreasing and the products are increasing. Also, stoichiometry plays a role. You see that the ammonia is going to be consumed, because of the stoichiometric coefficient 2, it's going to be consumed twice as fast as the nitrogen is produced. I also have to take into account the stoichiometry. And there's a pattern that we follow for doing so. So the rate, the quantity rate, I need to express it as a positive quantity, and I want it to be a unique number no matter whether I'm describing it in the terms of ammonia, nitrogen, or hydrogen. So here's the pattern. For reactants, we include a minus sign. This takes into account the fact that the delta concentration for a reactant is a negative number. The minus sign is going to cancel that out and make the rate positive. Okay, so that's the first part of the pattern. For products, we use a positive sign. So Delta N2 is going to be a positive number, so we multiply it by a plus 1, and that gives us a positive rate. Now, the other thing in here is the stoichiometric coefficient. So we see that we have a factor of 1/2 here for the ammonia, and a factor of 1/1 for the nitrogen, and a factor of 1/3 for the hydrogen. Notice that those correspond to the reciprocal of the stoichiometric coefficients. So it's always 1 over the stoichiometric coefficient for each species in the reaction, minus signs for reactants, plus signs for products. We have change in concentration over change in time. And these average rates are reflected in these slopes, so to speak. Okay. So notice that for this particular reaction, we started with no products, so the hydrogen and the nitrogen are both 0 initially, and we start with some amount of ammonia. Some ammonia reacts, and then that gives us some hydrogen and some nitrogen. Notice that the amount of hydrogen produced by a given amount of time is much larger than the amount of nitrogen that's produced, right? In fact, it's 3 times larger than the amount of nitrogen that we produced. So the stoichiometry is tied up in these slopes. And so we put the stoichiometric coefficients in the denominator here so that we can equalize them all and have one unique rate that is positive. Okay. So what you need to be able to do is to take any stoichiometric reaction that you're given and be able to write out these expressions and then solve little problems with the expressions. So let's do that. So here we have the reaction of ammonia with oxygen to produce nitrogen monoxide and water vapor. And so we're being asked to write out what are the expressions for the rate in terms of the rate of change for each reactant and each product. So we have rate equals, let's start with ammonia. It's a reactant, and so it gets a minus sign. 1 over the stoichiometric coefficient times the change in the ammonia concentration over the time interval. That's one equation. Now another equation we could write would be to set the rate equal to a change in the oxygen concentration. Oxygen is also a reactant, so we use a minus sign. 1/5 delta O2 delta T. Okay, so we've added one little equality here, but it actually added 2 equations. So one equation is to say that the rate equals this expression. The second equation would be to say that the rate equals that expression. And then the third equation that's hiding in here is that this expression equals that one. So this is a very compact way of writing 3 equations. And I could keep writing, but I'm running out of room here. So I'm gonna put the products down below. So here I'm going to start with the nitrogen monoxide. So I'll take plus, it's a product, 1/4, that's the stoichiometric coefficient, times the change in the NO concentration over the change in time. And then for the other product, it's plus 1/6, the change in the water vapor concentration over the change in time. And so this is actually a whole bunch of equations. So it's rate equals to each one of these. Moreover, each expression is equal to the other ones. And so we can use that in problem solving, as illustrated in this next problem. So here, they are telling us that the rate of formation of bromine is 6.0 times 10 to the minus 6 moles per liter. And that's a little bit of, there's some semantics here. What do they mean by the rate of formation of bromine? Well, bromine is a product here. And so the rate of formation of bromine, here, I'm going to do a new sheet of paper. And I'm going to write it out in words. So the rate of formation of bromine, and you could do this for any product, would be equal to the change in the bromine concentration divided by change in time. Notice I didn't put a stoichiometric coefficient in here. Let me illustrate the rate of formation of water. So, rate of formation of the water will be equal to delta H2O delta T. Didn't put the stoichiometric coefficient in here. Notice that the rate is not the same, the rate of reaction is not the same thing as the rate of formation of a particular species. When you're talking about a particular species, you leave the stoichiometric coefficients out. When you're talking about the rate of the reaction, which I'm going to do in a minute, you put the stoichiometric coefficients in. Let's do rate of consumption. Rate of consumption. Let's choose the bromide. That, we include the minus sign, but we don't include the stoichiometric coefficient. Okay, so the rate of formation of a product is distinct from the rate of consumption of a reactant, which is distinct from the rate of the reaction itself. Now, they are related mathematically, but they're different. Now, the reason we include the minus sign here is because the bromide concentration is going to decrease, and by definition, we want this to be a positive number. But we don't include the stoichiometric coefficient. For the H+, rate of consumption of H+, hopefully you got it, it would be minus delta H+ over delta T. Now what they've done in this problem is they said that this quantity, the rate of formation of bromine, is equal to 6.0 times 10 to the minus 6 moles per liter, and if you've been paying attention, you'll see that I've got a typo here. It should be moles per liter per second. I left off the per second. So we want to correct that. Now, the rate of the reaction. Here's where we include both the signs and the stoichiometric coefficients. So the rate of reaction, starting with the bromide, minus 1 over 5, delta Br minus delta T, that's one expression. Another one would be minus delta bromate concentration, delta T, equals to minus 1 over 6 delta H+ concentration, delta T. I'll put the products over here, plus 1 over 3, delta Br2, delta T, equals plus 1/3 delta H2O, delta T. Now, essentially what they're asking us to do is to express each of these rates in terms of that number. Okay, so we know this number. How is the number for water related to the number for bromine? Well, take a look at this expression here. This term equates to that term. You'll notice that the 1/3 cancel out. So it's telling us that the rate of production of water is equal to the rate of production of bromine, which makes perfect sense because the stoichiometric coefficients are the same. For every 3 moles of bromine you produce, you're going to produce 3 moles of water. So the answer for this one is 6.0 times 10 to the minus 6 moles per liter per second. Same number. It's going to be a little bit different for the other species, right? How would we relate? We want to relate now this number here, the rate of consumption of the bromide, to the value for the bromine. So what we'll do is we'll pick out this expression here and the expression for the bromine. Those are equal to one another. I'll work it out down here. Minus 1 over 5 delta Br minus over delta T equals 1/3 delta of bromine delta T. Now the number that I know is this number right here. That's the 6.0 times 10 to the minus 6. And I want to solve for minus delta bromide over delta T. I'm just going to move the 5 over. So it's going to be 5/3 times delta bromine delta T. It's going to be 5/3 times 6.0 times 10 to the minus 6 moles per liter per second. And so we can run that through our calculator. And you get 1 times 10 to the minus 5 moles per liter per second. You would do the same thing for the bromate and the H+. Okay, you would have to find the two equations that need to be set equal to each other, and then you have to solve for that rate of formation or the rate of consumption. Now the tricky part is dealing with the semantics. What's the difference between the rate of reaction and the rate of formation of a product and the rate of consumption of a reactant? So I've tried to articulate that here for you. Give it a shot, see if you can do that. This problem here is identical to that. Okay, so they give you the instantaneous rate of decomposition of hydrogen peroxide at a particular time. It has this value. Okay, so here's what they mean by that. Right, this is the rate of decomposition of hydrogen peroxide. It has that value. Then they want you to calculate the rate of production of the water and the rate of production of the oxygen. And so you need to take into account the stoichiometry in order to do that. You can almost guess what it would be. Right? Notice the stoichiometry is the same here between hydrogen peroxide and water. Okay? And so you would expect that the rate of production of H2O would be equal to the rate of consumption of hydrogen peroxide. Notice the 2-to-1 relationship here between hydrogen peroxide and oxygen. The hydrogen peroxide is going to be consumed twice as fast as the oxygen is produced. So you would end up dividing that number by 2. So you can think about it intuitively, or as I've done here in this example, you can follow the algorithm to derive the equations you need and then use the equations to find the particular rate that you need. Part B is the same. The only difference is you have to come up with the reaction for the decomposition of ammonia. I'll leave that as an exercise for you. This is something that you want to be able to practice and do. This is a very short section, so I'm going to go ahead and cover this one. Factors that affect reaction rates. Okay, so there are different factors that affect the reaction rate, and we'll talk about each of them in detail in further sections. So this is kind of an introduction to the rest of the chapter. One thing that affects the reaction rate is the identity of the compounds participating in the reaction. So for example, both sodium and calcium react with water to produce a basic solution and hydrogen. However, sodium reacts much more vigorously than calcium metal does. And so the identity of the compound of the reactants makes a difference. Another thing affecting the reaction rate is whether or not the reactants can come in contact with one another. So for example, when you're burning wood, the wood needs to react with oxygen gas. And if you're trying to light a wood block on fire with a lighter, a hand lighter, that's not very easy to do. What it does is just kind of chars and smolders a little bit at first. You're going to be waiting a long time before that wood catches on fire. And that's because there's not very good surface area contact between the wood and the flame and the oxygen. Now, if you cut that wood into small pieces, like kindling, or even better yet, if you grind it up into sawdust so there's a lot of surface area to come in contact with oxygen, the sawdust, catches on fire right away. And so that's the idea here between this point. Reaction rates depend upon temperature. In fact, they generally speaking will increase with temperature. A good rule of thumb, it's not a perfect rule of thumb, a good rule of thumb is that the reaction rate will double for every increase in 10 degrees Celsius. Sometimes it's more, sometimes it's less, but that's generally a good way of thinking about it. Another factor affecting the rate is the concentration of the reactants. The example that we're given here, we're comparing two reaction schemes. Calcium carbonate, which is limestone, which is often used to make statues, does not really react with water. Okay, it's generally speaking insoluble. It dissolves a little bit, but not a whole lot. However, if you've got an acid present, okay, so calcium carbonate in aqueous acid will react quickly, not super quickly, but it will react with the calcium carbonate to give you calcium sulfate, carbon dioxide gas, and water. This is one of the detrimental effects of acid rain. So if you have pollutants like sulfur dioxide, which comes from both industrial sources and also volcanoes as well, if you've got a lot of SO2 pollutant in the air, that's going to give rise to acid rain. Then the acid gets on the statues or on the limestone in the earth, dissolves it, and then that can lead to erosion, of course, which isn't good for statues, and it's not good for, you don't want to create sinkholes in limestone either. So try to keep the SO2 down if you can. Another thing that affects, and so if there's no, the point here being concentration, if there's zero sulfurous acid in the water that you're putting this chunk of limestone into, then the reaction won't occur. And it'll be the more concentrated the acid is, the stronger the reaction. For this last point, we'll talk about catalysts at the end. Catalysts, generally speaking, can dramatically increase the rate of the reaction. That's why they're so cool. And so we'll have a separate section on that at the end of the chapter. So I'm going to go ahead and stop this video here, and we'll pick up with rate laws in the next video.